Welcome back. Today we are going to talk about atomic history, meaning the history of the atomic model. How do we come to know what we know about atoms? It's going to be a pretty brief overview. Atoms, the word atom is actually a Greek word. There is a Greek philosopher named Democritus who came up with the idea of an atom as being the smallest, most indivisible piece of matter that makes everything else up. But Democritus's idea of what made up matter was not widely accepted at the time. Some people believed that everything was made up of 4 elements: earth, air, wind, and fire, and some gradient between Democritus's idea of atoms and Aristotle's adoption of the 4 elements. I'm not an expert on the subject at all, so I'm sure I'll put my foot in my mouth, but essentially there is a lot of ideas of what makes an atom. And then there is a few models that we have really built on in the last 200 years or so. And we're going to begin with Dalton's model. But just know that Dalton's model is not the first discussion that's ever happened on what makes an atom. But it is a replacement of the old idea of the Greek atom and building upon it. There's an acronym here for deadly turtles really bite. If you find that useful, then that's the order that these were discovered in. That's Dalton, Thompson, Rutherford, and Bohr. Those are the 4 scientists that you're going to need to know for Science 10. Dalton's idea replaced the ancient Greek theories about the atom. His idea was the billiard ball model. If you're unfamiliar with that, if you've ever played billiards or pool, you can think of a bowling ball. It's essentially just a hard sphere. He believed that all matter is composed of tiny indivisible particles called atoms. So he didn't change the word there. The Greek word was atoms. He stuck with it. And atoms of an element have identical properties. Now, this was a little bit of a revolutionary idea, this idea that, okay, well, everything's made of atoms, sure, but we have different flavors of atoms. So hydrogen has a different type of atom than oxygen, for example. Atoms of different elements have different properties. So atoms of hydrogen have properties that atoms of oxygen don't. Atoms of 2 elements combine in constant ratios to form new substances. So you can form compounds using Dalton's billiard ball model. And you can get a compound like, let's say, for example, water. We know that water has 2 hydrogens and an oxygen. I'm going to color code those. I'll switch the hydrogens to red. I have 2 hydrogens and an oxygen. Water has those atoms in it. And so using Dalton's model, you'd have 2 different types of billiard balls, but they're just solid spheres. And so you would have a solid sphere. I'm just going to shade it in to kind of show that it is solid. This is an oxygen. And it's somehow attached to 2 other solid spheres of hydrogen. But we don't know anything about these solid spheres. We just know that they are indivisible. This is the smallest form of hydrogen, this is the smallest form of oxygen, and they are going to combine in constant ratios. Dalton's model helped explain the law of conservation of mass. Now, this law states that matter, and specifically you can say mass, is never created or destroyed in a chemical reaction. So if you think of a chemical reaction, one that maybe got you to school today is gasoline combusting in a car. Matter is not being destroyed, even though you might experience that your car is losing that fuel, so it becomes lighter. But that mass wasn't destroyed. That mass was converted into a different form because those atoms broke apart inside the gasoline. If you were to have a big balloon on the back of your car and you caught all of the exhaust that came out of the engine, then you would have the same amount of mass if you weighed your car with the big balloon on it after combusting the gasoline as before. And this can be explained by having these constant ratios of atoms. They react by rearranging themselves. But they're solid spheres. Dalton, you can think Dalton equals Balton. That's dumb, I know. It's maybe a little irreverent of Dalton's name, but it helps me remember that Dalton came up with the ball model. Thompson. Thompson's model is the raisin bun model, sometimes called the plum pudding model. Thompson discovered electrons, and so now it's not just a solid sphere, we've got something in that solid sphere. So he observed cathode rays and their ability to be manipulated. He theorized that the material that makes up that cathode ray is even lighter and smaller than an actual atom, and it can be manipulated based on charge. This is where we're going to bring in the idea of positive charges and negative charges. So Thompson has the first model of an atom with electrons, and he thought that electrons are embedded within the atom like plums in a pudding or raisins in a bun. Here's a picture of plum pudding. I forgot this was in the notes. Here's another picture of plum pudding. Essentially, we have our atom still. So we'll take our atom. And our atom is mostly a positively charged mass, but embedded in this positive charge are little negative charges like raisins in a bun, or chocolate chips in a cookie, maybe, if you want to think of it that way. But the nice thing about this is a nice sphere, and you can see he thought electrons are embedded, stuck within there. That was Thompson's model. Rutherford. Rutherford's experiment was called the gold foil experiment. And it showed that there was a positively charged area of an atom called the nucleus. What he did was he took some positively charged alpha particles and he shot them through a sheet of gold foil. And he had a detector set up around that sheet of gold foil. And he found that some of the alpha particles bounced backwards, whereas many of them traveled straight through the gold foil. And it described it as like firing a gun at a piece of newspaper and having 1 in every 100 bullets deflecting back at you, which would be very surprising. And so he thought that the atom is mostly made of empty space because the particles would fly through, with the electrons moving outside the nucleus, but sometimes those positively charged alpha particles would hit a positive center, and because positives would repel those positive alpha particles, they bounced backwards or were deflected off the side. Sometimes this model is called the beehive model because you have this hive in the center and the nucleus are like bees flying around in random paths to occupy this empty space. What you have here, we have this nucleus which has protons and neutrons in it, most of the mass. It's not just positively charged, it also has most of the mass, and we already know from Thompson's model that the electrons are much less massive. So we're going to say this is our nucleus with protons and neutrons. And then orbiting the nucleus, we have electrons. Orbiting the nucleus. Now, Thompson didn't focus as much on the behavior of those electrons as our next scientist, which is Bohr. Bohr observed that there was differences in the atomic spectra. When we say the words atomic spectra, we basically mean the light emitted by excited electrons. That's an oversimplification a little bit, but Bohr observed that the same atoms would have the same wavelengths of light emitted if you excited the electrons, and he determined that each electron has a fixed amount of energy which is related to how close it is to the nucleus, its orbit around the nucleus. So Bohr came up with this idea, not just like Rutherford, where these electrons could be in seemingly just kind of a random moving around location. There's actually some organization to how they are orbiting around the nucleus. And he said electrons can only exist in certain energy levels, kind of like being on the floor of a hotel. There's not a room halfway between floors, or if you're at Center High, there's not a room halfway between floors. We've got 6 floors here. You have to move to a classroom on the 4th floor. You're going to have to go up or downstairs. You can't go to the 3rd and a half floor. Electrons can move between energy levels by absorbing or releasing energy. Can move between levels by absorbing or releasing energy. And this was the release of that energy is the atomic spectra that Bohr observed. Higher energy levels are further from the nucleus, so lower energy levels therefore would be closer to the nucleus. The first 4 energy levels can hold these amounts of electrons. This is going to be, we're going to look at these diagrams more in a future lesson, but this is important to remember that the first energy level can hold 2 electrons, and the second and third can hold 8 each, and the 4th can hold 18. I won't ask you anything past the 4th energy level. When an atom's outermost energy level is full of electrons, it is very stable and doesn't react. That's a pretty important phrase. I'm going to highlight that. When an atom's outermost energy level is full with electrons, it is very stable and doesn't react. This statement here is going to form the basis for why atoms form ions, trying to fill this outermost energy level with electrons. Bohr's model is sometimes referred to as the solar system model or the planetary model, with the electrons traveling around the nucleus, just like planets orbit the sun. Here's an example right here. We can draw a little simple Bohr diagram here. We've got a Bohr diagram that's full circles. You might also see a Bohr diagram later on in the notes, well, you will, that looks like this, where we have our nucleus here, and inside the nucleus you'll have some number of protons, some number of neutrons, and then around it, just above, you have these fixed energy levels that have electrons. This is a simplified version of this, where if you're looking here, you'll see here's our nucleus, which will have our protons and our neutrons. I'll write that down here. Have protons and our neutrons. And then in our first energy level here, these little dots represent electrons. We've got 1, 2 electrons. And then in our second and third energy levels, if you count them up, we have got 8 electrons in each of those. And yeah, down here, keep on going. Modern theories of atoms go beyond the Bohr model, but as far as Science 10 chemistry goes, we don't need to know so much about the electron cloud model or different orbitals and their geometry. Latest theories says that electrons are found in a cloud around the nucleus, and a lot of these clouds have funky orbits. It's an area where electrons are likely to be found, but you can never be sure exactly where they are and where they're going at the same time. But that's beyond Science 10. So in class, we're going to use the Bohr model. It's the easiest to work with, and it explains pretty well the chemistry that we're going to be doing at the Science 10 level. That's it for today. In our next lesson, we are going to cover some stuff on atomic number and atomic mass. In your work booklet, you'll see that there is a good amount of practice questions on pages 19, 20, and 21. I'd encourage you to try those out before watching the next video.